Okay, I want to go over the Chapter 15 practice test. I know it says Chapter 15 questions written on the document, but it's the practice test. So let's go over these problems, starting with the very first one, which says, okay, well, use that data below to find, well, KC is the question. So I'm trying to find KC. And there's a couple of things you should know about KC. KC is, I always forget what is it. It's either products minus reactants, products times reactants, products over the reactants, or some form of that. Well, as you should remember, KC, as well as KP, KC is the products over the reactants. The products, which are the NOBR, and because that coefficient, that'll be squared over the reactants, NO squared and BR. So that's the equation for KC. KC, which is the products over the reactants, 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 the products over the reactants. Coefficients 2, 1, 2. Squared to the first power squared. So those coefficients are the exponents. Okay, I need to plug in the equilibrium amounts. When we plug in into the equation for this is the equilibrium constant. So don't put in any initial amount, but I need to plug in the equilibrium amounts. Obviously in this table, it's blank right here, meaning we have to figure out what it is. Okay, let me rewrite this ICE table because I just, one, need more space, and two, it's kind of missing something in that table. And ICE stands for initial, change, and equilibrium. And that table, I'm missing the change part. So I'm going to fill in, I'm going to add a C for ICE. Okay, well, I'm given this is 2.5, that's 5.0, 1.0, that's a point, 2.0. Okay, so these are 3 or 4 data points I already know in the table that was given. Okay, well, I don't know what it changes by. Remember what we did before when we said, hey, let X be the change of one of these? Well, usually we say the reactants go down and the products go up. So we say, hey, this reactant goes down, minus X. This one will go down minus 2X. And the reason why? 2 to 1. 2 to 1. Okay. Reactants go down, the products go up. 2, 1, 2, 2, 1, 2. Reactants negative, products positive. Reactants negative, products positive. If you put this as positive, it would probably okay as long as the other side is negative, as long as it's opposite. Well, I kind of already know the change of this one because the initial amount and the change is equal to equilibrium, meaning 2.5 plus whatever the change is 2.0. So I know this change is negative 0.5. It goes down by 0.5. In other words, negative 0.5 is equal to negative 2x. And if negative 2x is equal to negative 0.5, x must be, or minus x, must be 0.25. So, well, another way to see it is this is BR2 will be half of whatever NO is. It's minus x minus 2x. So this is minus 0.5. This should be minus 0.25. So x is equal to 0.25. If x is equal to 0.25, 2x would equal to 0.5. Or you can see that as negative 2x, which is negative 0.5, is equal to, and this is positive 2x, or positive 0.5. The initial amount plus the change amount is equal to equilibrium amount. 5 minus 0.25 is 4.75. 1 plus a half is 1.5. So now I have this data table filled out. I know the equilibrium amounts of each thing, NO, Br2, and NOBr. I could plug into the equation the equilibrium amounts. Kc is equal to NOBr, which is 1.5, squared over NO, which is 2.0, squared times Br minus, or not Br minus, just Br2. That is, oh, that should be Br2 there, 4.75. And so, type that on a calculator. What answer do you have on a calculator for this? Well, when I did it, assuming I plugged that in a calculator correctly, I got 0.118. So Kc equals 0.118. What are the units of Kc? Kc and Kp have no units. The equilibrium constant are dimensionless. So don't worry about the units. There are none. Okay, going on to the next one. Okay, problem number 2. It says, consider this reaction. Okay. 2 moles of ammonia makes a mole of nitrogen and 3 moles of hydrogen. The equilibrium is set to be established as 1.0. Is established in a 1 liter container at 1000 kelvins, where Kc is 4.0 times 10 to the minus 2. Initially, 1220 moles of ammonia are present. Estimate the equilibrium concentration for hydrogen. Okay, this is another one of these ice things. So this is another type of ice problem. So, okay, hold on one second. Okay, so, well, maybe let's set up some ice table. So I know that I have, let me rewrite the equation. 2 moles, oops, that should be, 2 moles of NH3 makes 1 mole of N2 and 3 hydrogens. This is a ice thing. Okay. Well, what do I have initially? It says you have this reaction. Initially, you have 1220 moles of NH3 present in a 1 liter container. Molarity, which is moles over liters. The number of moles is 1220. I know it's just divided by 1. So the molarity is obviously 1220 molars. So the molarity of NH3 is 1220. And nothing else. Initially, all you have is 1220 molars of ammonia and nothing else. Well, this will decrease and these will increase. Minus 2x plus x plus 3x. Why? 213. 213. Negative for reactants, positive for products. Negative for reactants, positive for products. The initial amount plus the change amount is equilibrium amount. The initial amount plus the change amount is equilibrium amount. So this will be 1220 minus 2x. 0 plus x is just x. 0 plus 3x is just 3x. Now I have my ice box, in a way, filled out. Also, just commonly known as ice boxes. As you can tell, ice and then a whole bunch of boxes. Okay, so this thing. Now let's set up the equation. Kc, which I'm given. Kc is products over reactants, the products over the reactants, the products over the reactants, the products N2 and H2 cubed over the reactants NH3, ammonia, squared. Products over the reactants. So what do we do now? Now we just have to plug in all these things. Well, first of all, Kc was given. It was 4.0 times 10 to the minus 2 is equal to the nitrogen amount, x, times hydrogen amount, 3x, cubed. all over 1220 minus 2x squared. Okay, once we do that, now the hard part, find x. Okay, now the hard part is to find x. I'm just going to write the answer of what x is right now, but I will show the work towards the end. Okay, I'm just going to tell you right now, x is 6.8142, because I've already done it, but I will do the work afterwards. Okay, so I found x. X is 6.8142. Okay. Once you know x, okay, so basically, let me just circle this thing. I just want to say find x. Okay, found it. But I will do the work after. So now what? Once I find x, this is actually really easy. The question is, what's the hydrogen concentration at equilibrium? The hydrogen concentration at equilibrium is 3 times x. X being 6.8142, or that is 20.4. Don't worry about sig figs right now, but 20.4. I'm sure there's other digits. And units are molarity for concentration. 20.42. Okay, I know the hard part is actually doing the math. Let me explain it, but this is not going to be fun math. There might be a problem like this on a test, but do realize it's just math. Let me explain how I did it. I did this on a separate sheet of paper. Actually, I did it on Post-its. So here was my amazing work on this. So what do we have? First of all, hold on. Let me just one step at a time. Okay, I know it's backwards or flipped on that side. Okay, 3 times, or x times 3 cubed. 3 cubed is 27. X times x to the third is x to the fourth. All over, just copy 1220 minus 2x, parentheses squared, is equal to 4 times 10 to the minus 2. Since I have to the fourth power and squared, I could take square root of both sides. Square root of that is 0.2. But square root of something squared is plus or minus. So I have 5.196x squared over 1220 minus 2x, because square root of 27 is 5.196. Okay, well, I did it first in terms of the positive value of x. Distribute both sides to the denominator, or multiply both sides by the denominator, combine like terms, and I have this. Plug into the quadratic equation. I got 6.8142, or negative 6.8912. Maybe I copied it wrong, but whatever. Either way, not the negative one. Why not the negative one? Because the value of these nitrogen and hydrogen at equilibrium, nitrogen and hydrogen at equilibrium are x and 3x. They have to be positive numbers at the end. So no matter what, not the negative one. In case you're wondering, well, what if I plugged into negative 0.2? Okay, I've also done that, since you asked. If I plugged in as a negative 0.2, solving for x, I get 2 values for x. Either way, both of them with imaginary numbers. If I can't even have negative for x, what makes you think I can have imaginary numbers for x? So definitely not that. Okay. The answer is the positive 6.8142. So either way, do whatever math you got to do. Do whatever math you got to do to find x. Found it. Once I find x, I can figure out the hydrogen or nitrogen. This question is about hydrogen. I can find a hydrogen concentration, which is 3 times that x. I kind of actually already did the question number 3, which I think is the number is the next page. Let me get the paper. It's the exact same question, except question number 3. Question number 3. Find the nitrogen concentration. Is exactly word for word the same thing, except this time find a nitrogen. What's the nitrogen concentration? It's x. What's X? 6.8142. I'm not doing that again. The nitrogen concentration, 8142. 6.8142 molars. That's the answer for number 3. So that's what I meant by I wasn't going to do that again. Okay, next question. Next question is number 4. Consider that reaction. Okay. The equilibrium constant is... Oh, in case I had to do this again. Now, this question is not asking about equilibrium amounts at the end. It says, what's Kp? There's one other equation in this chapter. Kp is equal to Kc times RT to the delta n power. I'll give you R in a test, but R is equal to 0.0821. Don't worry about the units because we don't use units for Kp or Kc anyways. So I know R, also know the temperature. Where is the temperature? Oh, good. Temperature is 1,000 kelvins. Temperature does need to be in kelvins, and it already is kelvins. Only other thing, delta N. Delta N is coefficients of the products minus the coefficients of the reactants, summed up. Coefficients of the products minus the coefficients of reactants. The products, 1 plus 3 or 4. 1 plus 3 or 4 minus coefficients of reactants, 2. 1 plus 3 or 4 and coefficients of reactants, 2. Delta N is positive 2. Okay, plug it in. Kp is equal to Kc, which was 4 times 10 to the minus 2, times R times T to the delta N power. Type that on a calculator. I got 270. Okay, this is fun, isn't it? Okay. Next one, number 5. Question number 5 says hydrogen iodide decomposes according to that equation. And okay, 0.66 moles of sample hydrogen iodides injected a 2-liter vessel at 400 degrees Celsius. Calculate the concentration H2 at equilibrium. Yet another ice problem. So let's copy that down. 2HI makes H2I2. Okay. Okay, what do I know? Well, I kind of know the molarity of this thing. I have 0.66 moles in a 2-liter container of HI. Molarity is moles divided by liters. I'm not showing that work. That moles divided by liters, 0.660 divided by 2 is 0.33. Okay, that's the initial amount of hydrogen. And I got nothing else in the container. I do want to, at the end, find this amount here. Equilibrium amount of the hydrogen. So whatever it is in there, that box is what the question's asking. Okay, we usually say reactants go down minus 2x because it's coefficient 2 plus x plus x. Okay, minus 2x plus 1x plus 1x. That's my ugly handwriting. This is plus x and plus x. Initial amount plus change amount is equilibrium amount. 0.330 minus 2x. That's just x, and that's x. Okay, so now I have this ice table done. Now I can write the equation for Kc. Kc, which is products over reactants, the products, hydrogen, iodine, over the reactants, Hi squared. Products over the reactants. What is Kc again? Wait, it was, it was given. It's right here. Kc is 0.0156. It's equal to hydrogen, which is x, times iodine. or x squared, over 0.33 minus 2x squared. Okay, now do whatever you got to do to solve for x. Okay, do whatever you got to do to solve for x. I've already done this, so I'm just going to write it. X is equal to 0.03296. And don't worry about sig figs. Okay, but I found x. And I will show the work afterwards. But find x. Probably the easiest thing is, well, multiple ways of doing it. You could take square root of both sides, since it's squared over squared. And then that's one way to do it. But I think I did another way. Okay, but either way, find x. The question is, how much is the hydrogen amount at equilibrium? It's x, right there. It's x. X being 0.03296. And the units are molarities. So that is the hydrogen concentration. How did I solve for x here? What I did was, what did I do? I changed that equation. Okay, multiply both sides by the denominator. So I got that. Distributed or FOILed the whole thing. That's times 0.00156. Combines like terms. Then I have the form ax squared plus bx plus c is equal to 0. And then I use the quadratic equation. So I did not say it's easy. In fact, the most difficult part of doing all this ice stuff is finding x. Okay, setting it up usually is not that bad. Products over reactants is equal to k. But find x, however you got to solve for x. That's just purely algebra, and you're going to have to figure out the algebra part yourself. Okay, thank goodness the next few problems have no math on them. Yeah, I don't think any of the rest of the problems have math. So we're kind of done with the math part. The rest is all the Le Chatelier's principle stuff that does not have any math in it. So question number 6 says, consider equilibrium equation. Carbon and water and energy or heat makes carbon monoxide and hydrogen. What will happen to the concentration of carbon monoxide, CO, that one, if the temperature system is raised? Okay. Maybe I should say, I'm going to rewrite this. Who cares what the number is? That's heat, okay, or energy. Okay, that's heat or energy. If we raise the temperature, we're adding heat to this thing. We're adding heat to this thing. So we're adding some reactant. If we're adding heat, there's only two things reactions can do, shift to left or shift to right. And if you want to get rid of heat, the reaction will need to shift to the right. And what does it mean to shift to the right? That means everything on the left side will decrease and everything on the right side will increase. When we say shift to the right, everything on the right side increases and the left side decreases. I mentioned before, it's kind of like a seesaw. If one side goes up, the other side must go down. So one side goes up, one side must go down. If it's the other way, if one side goes down, the other side must go up, like a seesaw. So the question is, I know it's going to shift to the right, so everything on the right side will increase, everything on the left side will decrease. What will happen to carbon monoxide? Well, it's on the right side. It's going to increase. So carbon monoxide will increase because it's on the right side of the arrow, or right side of the equation. So carbon monoxide will increase in that reaction. Okay, number 7. It's actually the same equation. What will happen? So given the same equation, if we add water, that thing. Okay, if gaseous water is added to the mixture, what will happen to the temperature of the mixture? Remember, this is heat. I'm going to change that to the word heat. Okay, so the first thing is, if I add water to this thing, it wants to get rid of it. It gets rid of it by shifting to the right. So it was going to shift to the right. If this reaction shifts to the right, then everything on the left side will decrease and everything on the right side will increase. Well, heat is on the left side. Heat is on the left side. If I decrease everything on the left, decrease heat, what will happen to the temperature? Well, the temperature or the heat decreases, so the temperature must go down. So the temperature goes down. Because we're going to be using heat or we'll be removing heat. You remove heat, it gets colder. Okay. Next one, number 8. Consider that equation. They're all the same equation, I just realized. Okay, so doesn't matter. Given that equation, what happened if carbon was added to the system? Okay. If carbon is added to the system. Okay, this one is, yeah. What happened to mass of carbon? Oh, sorry, I'm reading the question wrong. We didn't add carbon. Well, what happened to carbon? Not that carbon's increased. Well, what happened if we add water? Okay, so we're adding water. Reaction will either shift left or shift right. Okay, if we add water is the stress. The reaction wants to get rid of it. It will get rid of it by shifting to the right, is what the reaction will do to get rid of water. So everything on the left side will decrease and everything on the right side will increase. And what will happen to carbon, which is on the left side? It will decrease. So carbon will decrease. Okay, number 9. Same equation. Consider that equation. What will happen, and which way will the reaction shift if the pressure is increased? Okay, now the question is, what direction will it shift? And there are only 2 options, left, right, or doesn't matter, or doesn't shift either way. And so, if the pressure is increased, it wants to go to the side, the left side or right side, that has less gas pressure. So which side has less gas pressure? Well, on the left side, I have 1 mole of gas. And on the right side, I have 1 plus 1 moles of gas, or 2 moles of gas. In case you're like, what about the carbon? You see that S there? That's not a gas. S stands for solid, as you probably know. S stands for solid, so that's not a gas. If we increase pressure, once it goes to the side that has less pressure, which side is there less gas? The left side has less gas. The reaction will shift to the left. Now, I said things will shift left or right or neither if it doesn't change, or if it doesn't help in either way. What I mean by that is, if this was a gas, I just changed that from solid to gas now. If that said gas there, not solid, if that said a G, then it would be 2 moles of gas on the left, 2 moles of gas on the right, 2 moles of gas on the left, 2 moles of gas on the right, then neither side is favored. If they were 2 moles of gas on both sides, and we increase the pressure, in that case, it will neither shift left nor right, because it's the same on both sides. 2 moles of gas on the left, 2 moles of gas on the right. It will make no difference. Okay, 2 more problems, and I don't believe it's real. Oh, well, kind of, not really. Oh, that's not math. Okay, number 10. What's the correct equilibrium constant for this expression? Technically, there's 2. Kc is equal to products over reactants squared. Because coefficient 2 squared, coefficient 1, 1, so the first power, first power. As I said, there's technically 2, because that's Kc. There's also pressure. Why? You apply that if they're all gases. So we do these for the gases. That would be the pressure of the products over the pressure of the reactants. But either way, products over reactants, products over reactants. Pressure, if it was in atmospheres, if they're gases, and then concentration in molarity. So, and this doesn't ask, but as you should know, Kp is equal to Kc times RT to the delta N. It doesn't ask in this question, but you should also know that. Okay, one last Le Chatelier's principle problem. Consider following equilibrium. Okay. State whether each of the reactants will increase, decrease, or remain constant when the temperatures increase. Whenever you see these things, I just put that as heat. Who cares how much heat? But it's fine. 1531 joules or kilojoules. Okay, if we increase the temperature or increase the heat, it wants to get rid of heat. So to get rid of heat, the reaction will shift to the left. Shift to the left. Everything on the left side will increase, and everything on the right side will decrease. Now the question is, what will happen to each of the reactants? Reactants on the left side, they will increase. Okay, so that's it for the practice test. And so the test is going to be next class on this stuff. And I'm sure you'll have lots of fun on it.